Hi, I'm Philip, and I'm now going to talk about compact oblivious routing in weighted graphs. Let's start with routing. So we are given an undirected graph, and we are given some number of source-target pairs. For each of these pairs we have a demand, so that's the amount of flow that we want to route from that source to that target. We route these demands. That means that we compute a flow for each of them, and that flow sends the specified amount of packets from that source to the target. Now let's make this a bit more difficult and consider oblivious routing. Here we are not given the demands. So we just have the source-target pairs, and we have to compute flows based on that. We don't know how many packets will actually be routed from the source to the target. Also, we want to be compact. That means that we want to be able to route the packets while using only a small amount of routing information. So we will not specify the flows directly, but instead we will give a routing algorithm which can be used to compute the flows and which can be used to route the packets. So what's a routing algorithm? A routing algorithm basically encodes the local forwarding decision made while routing a packet. So we have some packet incoming at a node, and on that packet we have the packet header. So that's information stored in the packet. It's used for routing. Then at the node we have the routing table. This is static routing information specific to the node. These are taken as input by the routing algorithm, which computes a new packet header, which replaces the old packet header, and it computes the outgoing edge. So we will forward the packet along this edge. Initially, we set the packet header to be the node label of the target node. So we do that, we inject the packet somewhere into the network, and then we repeatedly do the local routing using the routing algorithm. So we execute the routing algorithm, we update the packet header, and we forward the packet along that edge. We do that until it has reached its destination. This then specifies a flow through the graph. So it's a flow from the source to the target. Note that the routing algorithm might be randomized. So it's possible that we are dealing with a probability distribution over outgoing edges, and we actually get a proper flow out of this instead of just a single path. So what do we want to achieve with our algorithm? There are two things. We want the algorithm to be competitive, and we want to have a low space complexity. So for the space complexity, we are looking at the size of routing information. So there are the node labels, there are the routing tables, and the packet headers. All of these should be short. The node labels, I should note, these are chosen by us, so we can store a small amount of routing information within the node labels. There's also the so-called name-independent model, where the node labels are chosen by an adversary, so you can't use them to store routing information. However, we are not doing that. We are choosing the node labels. Regarding the competitive ratio, there are two possible cost measures you can look at. So both of these are based on the load. The load of an edge is simply the amount of flow traversing the edge divided by the weight of the edge. And there are two kinds of cost measures related to this. There's the total load, that's the sum of all loads, and there's the maximum load, which is the maximum of all loads. This is also called congestion. For the cost measure total load, there have been many results on this. So if you're doing shortest path routing, which optimizes for total load, this is already oblivious. There has been a lot of research into this cost measure, specifically into doing compact routing schemes, optimizing for total load. So this is a selection of results. In particular, there have been trade-offs identified between the competitive ratio of the algorithm and the amount of routing information that you need. So that's the cost measure total load. However, for the cost measure congestion, there's only been one result. So there's only one result on doing compact oblivious routing when considering congestion. So that result is by Recker and Schmidt. They use a hierarchical decomposition. We're going to look at that in a moment. And they achieve basically polylogarithmic guarantees across the board. The exception to that are the routing tables. The size of the routing tables depends on the degree of the node, so on the number of incident edges. There's also a big drawback to their results, and it's that it only works in unweighted graphs. What we are going to do is we are going to extend the result to work also in graphs with polynomial weights. So this is our final result. You take any undirected graph with polynomial weights, and then you can construct an Oblivious routing scheme where basically everything is polylogarithmic. For the size of the routing tables, we also have the dependence on the degree of the node. This is, again, the number of incident edges, so this is the unweighted degree. It does not count the weight of the adjacent edges, just the number of them. We are also, again, only considering polynomial weights. You could also imagine graphs with exponential weights, but we're not doing that. Now let's move on and talk about the decomposition tree. So we start with a single cluster containing all vertices. We then split that into multiple children, each containing a subset of vertices. Then we do that recursively, so each of these children will be split up further and further until we get a decomposition tree. At the leaves of this decomposition tree, the clusters contain only a single node. So the leaf nodes in this tree are single node clusters. That means that if we want to route from one node to another, we can identify two clusters in this tree as the source and the target. So now let's imagine that we want to route from the source to this target. We do this by going up the tree. So we start with a packet in the source node, and then we want that the location of the packet is chosen from a probability distribution so that it's randomly distributed in the parent cluster. So the way this works is that we pick a random node in the parent cluster and we send the packet to the random node. So after the step, the packet is randomly distributed in the parent cluster. We do the same thing, so now the packet starts being randomly distributed in the parent cluster, and we want that the packet is randomly distributed in the grandparent. We do that until we reach the common ancestor of the source and the target node in this tree. Afterwards, we do the same operation in reverse. So now the packet starts out being randomly distributed in the parent cluster, and we want it to be randomly distributed only in the child. So we are taking the probability distribution and we are concentrating it only in the nodes belonging to the child cluster. And again, we do that until we've reached the leaf, at which point there's only a single node in the cluster and the packet has arrived at its destination. To implement this, we need two operations. The first one we call mixing. That's where you start with a packet randomly distributed in a child, and you end up with a packet randomly distributed in the parent cluster. There's also the reverse operation, so going down in the tree, where the packet starts being randomly distributed in the parent and ends up in the child. These are the two things that we have to implement. Mixing is a lot easier to implement, so we're going to look at that first. Also, due to the properties of this decomposition tree, if you implement these two operations, the mixing and the unmixing operation, you basically can route packets competitively. So the precise way this works was already constructed in the result by Recker and Schmidt. So we are not going to look at that in detail. We're just going to implement the mixing operation and the unmixing operation. So from now on, we are only going to look at the single parent cluster and the children, and then implement these two operations. Now let's look at how this is, so the mixing operation in particular is implemented in unweighted graphs by Recker and Schmidt. So they compute a single multi-commodity flow, solving this problem for all the children at once. So this multi-commodity flow routes each child distribution into the same parent distribution at once. You can do this with low congestion due to the properties of the decomposition tree. Then they don't want to store flows because that takes a lot of information. Instead, they use randomized rounding. So they pick a path at random from the flow, so with the probability of the flow. And doing that doesn't increase the congestion by much, and you end up only having a few paths for each edge. because the edges all have weight 1. So if you would have lots of paths, you would also have a high congestion, but you don't. So there are only a few paths. And then you can store the routing information for these paths directly in the graph. So in these edges, you store routing information for the paths traversing the edge. Well, to be more precise, you can't store the information in the edges, you store it in the adjacent nodes. And then you end up with storage for each of these adjacent nodes, polylogarithmic in the degree of the node. So that's where the dependence on the degree comes in. The problem in weighted graphs is that in a weighted graph, you might have lots of paths traversing a single edge. They still have a low congestion because the edge has a large weight. So we can't store the routing information in the nodes adjacent to this edge because that would be too much routing information. All right, now we're going to look at single commodity flows. We'll later use them as a building block for more complicated constructions. So actually, let's look at a multi-commodity flow first. So in this picture, we have multi-commodity flow routing some units from the left to the right. If we zoom in on one of these nodes, then we can see that there are some incoming units of flow and some outgoing units of flow. So first, we assume that the flow is integral. So it only uses integer amounts of flow. We can do this without too much of a problem by just rounding the flow if it's not integral. Then we treat each of these units of flow as a separate thing. So if you want, you can imagine a separate packet for each of these units. We assign all of these unique identifiers. These will be integers chosen so that they're unique. It doesn't really matter. We do that for the outgoing edges. So we choose intervals for each outgoing edge, which contains just the right amount of unique identifier. So we know which packets arrive at this node. So we simply have to choose the thresholds such that the correct amount of packets is forwarded along each edge. And then the only thing that we have to store are these intervals. So we just need to store upper and lower bounds and can route a large amount of packets along these edges. Now the problem is that if we are doing that, we cannot really ensure that different commodities go where they're supposed to go. So in this specific example, you could think of identifiers and intervals so that it would work, but in more complicated examples, it's not clear how you would do that. So looking at the original graph, we now have a few packets ending up at the wrong target. So that's a problem. And basically this means that we can only use this procedure for single commodity flows. So for a single commodity flow, of course, it's not a problem if the packets end up somewhere else because there's only a single commodity. So you have to keep in mind, if we do this, that we can't control where the packets end up. However, what we can do is we can ensure that the correct amount of packets lands at the right target. So each target gets the correct amount of packets. Now, is this enough? So can we use this to implement a mixing operation? So we could compute a flow for each child cluster, and then we could do this procedure to route the single commodity flow for each child cluster. However, there's a problem, and that's that we have too many child clusters. There could be lots of child clusters, and then we can't store these flows in the parent because they would take too much routing information. So actually, this doesn't quite work. Now let's look at random walks. So we are using cut matching games. That means that we are now playing a game which has a low number of rounds, to be precise, a polylogarithmic number of rounds. In each of these rounds, we are given a cut. The cut separates the graph into two sets of equal size. And then we compute a matching, a bipartite matching, which respects this cut. This can be any matching. So later on, we'll have to route that matching, so there are some restrictions. But for the purposes of cut matching games, we can choose any matching. doesn't matter which one. After we've done that, after we've chosen all of these matchings, we can execute a random walk. So we have a packet, the packet is at some node, and then we iterate through the matchings. For each of these matchings, we throw a coin, and depending on the result, we either switch to the other side of the matching or we don't. We do that for all the matchings, and then we end up randomly distributed in the graph, so uniformly distributed across all nodes, regardless of which node we started in. So each node performs a random walk and ends up uniformly distributed. But the problem with matchings is that they're symmetric. So we have to be able to route in the same way in both directions, and that seems difficult. So instead, we are going to use single commodity flows. So we compute a flow, one for each direction, which sends one packet from each node on one side to each node on the other side. We don't really know where the packets end up. So this is not a matching, it's not symmetric. You could think of this as two directed matchings if you want. The important part is that if you do this with single commodity flows, the procedure of cut matching games still works. So we still get a random walk out of it. And we only need to implement a polylogarithmic number of flows, because that's the number of rounds in the cut matching game. So now that we have a random walk, we can do the mixing operation. So we embed this random walk once for the parent cluster, so only once. And then if we want to execute the mixing operation, we simply send the packet on the random walk, and then it ends up randomly distributed in the parent cluster. All right, so that's the mixing operation. Now let's talk about unmixing, which is the more complicated part. The basic problem is that we might have lots of child clusters, so we can't store information for each child cluster. That would be too much. We have to compress that in some fashion. Recker and Schmidt use hypercubes for this purpose. So they assign each child cluster some range of hypercube IDs. And they do that in some fashion so that they know which child cluster gets which IDs, and that this information can be stored very compactly. So we can now assume that we know which hypercube IDs belong to a child cluster. And then the idea is that instead of routing to the child cluster in the original graph, we simply route to the child cluster in the hypercube. So we pick a hypercube ID belonging to the child cluster and route to that. So by assigning the hypercube IDs to the child cluster, each node gets roughly its degree in hypercube IDs. So that's a low amount. And of course, in the hypercube, each node only has a logarithmic number of neighbors. So when routing in the hypercube, it's easy to compute the route in the hypercube graph, and then you only need to execute this route in the original graph. But for this, it's sufficient to know where your neighbors in the hypercube are. So each node only needs to store a logarithmic number of neighbors per hypercube ID that it is assigned. So in total, you only need a polylogarithmic amount, polylogarithmic in the degree of the node, number of hypercube edges which you have to be able to route for each node of the original graph. So again, we run into a problem in weighted graphs. So actually, the number of hypercube IDs isn't bound by the degree of the node, but it's bound by the weighted degree. So the degree is the number of incident edges. Weighted degree, of course, is the sum of all adjacent edge weights, which can be quite large in unweighted graphs. So we'd have to have lots of hypercube IDs, and this doesn't really work because now we'd have to store lots of hypercube edges for each of these nodes. Instead, we are implementing a logarithmic number of hypercubes with different weights. So we round the number of hypercube IDs a node should receive. We round that to be a power of 2, and then we can group the nodes into classes. So these classes then form the weights of the hypercubes. These are disconnected. For each class, we have a single hypercube, which is simply an ordinary hypercube, and during routing, we can pick one of them. As a consequence, each node only gets a low number of hypercube IDs. Now, what does it mean for a hypercube to have a certain weight? Basically, the weight of the hypercube corresponds to the amount of flow we expect to send over a hypercube edge. So if a hypercube has weight 1, then we would expect to be able to send 1 unit of flow over a single hypercube edge without causing excessive congestion in the original graph. So for now, let's assume that we have such a hypercube. So the hypercube edges have weight 1. Now, what do we need to do? Again, each node has some number of hypercube IDs, and it needs to store routes to its neighbors in the hypercube. So in the hypercube, it has some number of neighbors, and it needs to reach these in the original graph. So this creates some number of demands in the original graph, some number of source-target pairs corresponding to the hypercube edges. For each of these pairs, we can now again use randomized rounding to get a single path. Now, this graph might seem familiar. We end up with the same problem we had earlier. Even if we have to only store a single path for each of these demands, we still don't know how to do that. It might be that there are edges which have lots of paths, and then we can't store the routing information for each path. And again, we use the random walk to solve this problem. We combine this with Valiant's trick. So we want to route from a source to a target. And we first do a random walk, which ends up at some intermediate node. Then, from that intermediate node, we again do a random walk, but we want to end up at the target node. So we only pick among the paths from the random walk which lead us to the target node. You could say that we condition the random walk on ending up at the target node. So we have picked a random intermediate node, we have a random walk going from the source to the intermediate node, we have one going from the intermediate node to the target. This is just Valiant's trick, and the standard analysis of Valiant's trick guarantees us that that the congestion increases only by a factor of 2. So we have a good congestion doing this. And importantly, both of these paths are generated by random walks, which means that we only have to store the coin flips, so the random decisions we made during the random walk. So again, the random walk means that we have the matchings and we decide whether to go to the other side of the matching or whether to not do that. Those are the coin flips. And there's a small number of them, so there are only polylogarithmically many of them, which means that we can store the results of these coin flips in the source node. So all of them will be written onto the packet, and when doing the actual routing, we are not flipping any coins, we are using the results we've stored in the packet. So in the source node, we've stored the coin flips. And that's enough to store the routing information we need for the path. So we don't actually need any additional information, so besides the random walk, besides the information necessary for the random walk, we don't need any additional information in the graph. However, this does not work for the hypercubes which have a large weight. In this example, we want to route a lot of flow from the source to the target. And there are lots of small edges in between, so it's possible to route this amount of flow, but it's not possible with a single path. We have to use multiple paths. If we were to send the packet along a single fixed path, then that would cause a large congestion on the path and it would overload one of the edges in the middle. So we actually have to store multiple paths for this. And that's a problem. So while we can store enough routing information to route a single one of these paths, again using the coin flips, we cannot store enough routing information for all of them. So the way to solve this is that we use these intermediate edges, separating these two nodes, to store the routing information. So the problem only appears if we have a source and a target exchanging a large amount of flow, where there are lots of small edges separating the source and the target. And these small edges, or rather some nodes adjacent to them, will be used for storage. All right, how does this work in detail? So let's consider some source-target pairs, some demands. These correspond to hypercube edges. So these demands correspond to the hypercube edges that we want to embed into the graph. Then for each of these demands, we use the procedure with random walks and Boolean trick, which I just described, to construct paths. So each of these paths can be encoded using only the coin flips. So we only need to store the coin flips for a single one of these paths. However, we have many of them, so we can't store all of them at the source. Now, because there are many paths, there have to be many edges in the middle separating the source and the target, and we can identify intermediate nodes. So these are just nodes adjacent to these edges. We want to use these nodes for storage. So instead of storing enough routing information to route to the target directly in the source node, we will only store enough routing information that we can reach one of the intermediate nodes. For this to work, we have to look at the weight of the intermediate edges, and again we round them to be a power of 2, and then that's the class of the edge, and we only have a logarithmic number of classes. And then we group the demands based on the class of the intermediate edges. So now that we've done that, we consider a whole group at once. So here these are the two demands of the group, and we compute a single commodity flow going from the sources to the intermediate nodes. And then in the source we only have to store enough information, which basically says use the single commodity flow to reach one of the intermediate nodes. Now that we've done that, we can route a packet from the source to one of the intermediate nodes. And then what we do is we route the packet backwards to the sources again. So this is a bit counterintuitive. What we would like to do is we'd like to go from the intermediate node directly to the target. However, there's the problem that, again, this is a single commodity flow and we cannot keep the commodities separate. So the packet might end up at a different destination than was intended. In particular, a packet here of the second source might end up at an intermediate node, which originally belonged to the first source. And it's not clear how to route from that intermediate node to the target which we want. So instead of going to the target, we go back to the source node, and there again the packets might not arrive at the original intended destination, so the packet might arrive at the other source. What we then do is we introduce new demands. So for each of these packets we introduce a demand which goes from the packet, from the source the packet is now in, to the target the packet should reach. In this example, all the new demands will have size 1. So all of these new demands we can route using a single path. And then, again, we do the same thing. We do the random walk. We use Valiant's trick. So the path can be encoded by storing the result of the coin flips, which is very short. And this short amount of routing information is something which we can store. And we store that in the intermediate nodes. So the packet is sent from the sources to the intermediate nodes, and there it picks up this routing information and remembers it for later. Then it goes back to the source nodes, and now it can use the routing information to go to the target. This works because the demands here have size 1, so we are guaranteed to route them using a single path. In general, we only know that the demands have gotten smaller because we have split them up over multiple intermediate nodes. We know that the size is decreased. We don't necessarily know that we can route them using a single path. So it's possible that we need to apply the scheme recursively. So we split up the demands, and then we route some of them using a single path, and the others we split up again. And the information for that then will be always stored in the intermediate nodes. And finally, we can route them using a single path, which again is stored using the coin flips in the intermediate nodes. And after that stage, we're done. And because the demands always get smaller, we are guaranteed to terminate after some number of iterations. And we can even guarantee that the number of iterations is small, that it's only polylogarithmic. So in total, we only need to implement a polylogarithmic number of single commodity flows, and then we get a good congestion, and the amount of routing information is also guaranteed to be small. All right, that's all I wanted to say. Thank you for your attention.